Back at the turn of the 20th century, physics felt pretty much settled. We had these amazing rules for gravity, for motion, really for everything you could see. But see, there were these little nagging problems, these strange clues piling up from the world of the super, super small. And these weren't just going to rewrite the rules. They were about to blow up our entire picture of what reality even is.
All right, so to really get this, let's just compare the two worlds we're talking about. On one side, you've got our everyday classical reality. Things are solid, they're predictable, everything flows smoothly. But on the other side, you've got the quantum world of atoms and electrons. And that world, it's all about probabilities. It happens in these little chunky steps and, well, it's just plain weird.
So our whole detective story really kicks off right here. We had the laws of classical mechanics, and they worked beautifully for things like planets and cannonballs. But when physicists tried to use those same rules on the tiny world inside an atom, they just started to break. The math didn't work anymore.
And that's the thing, right? This wasn't just some minor tweak. As scientists looked deeper and deeper into the fabric of matter, they realized the old rulebook wasn't just missing a few pages. In a lot of cases, they had to pretty much toss the whole thing out and start from scratch.
Okay, so the first huge clue in our mystery comes from a physicist named Ernest Rutherford. He really wanted to figure out what an atom actually looked like on the inside, so he came up with a brilliant idea. Let's shoot something at it and see what happens.
And the experiment he designed was just genius. His team fired a stream of tiny, positively charged bullets. These are called alpha particles, at a ridiculously thin sheet of gold foil. Seriously, you can think of it like firing a machine gun at a single piece of tissue paper.
So what did they think was going to happen? Well, the popular model back then was called the plum pudding model. They imagined the atom was just this soft, puffy cloud of positive charge, with electrons dotted inside like plums. Based on that, they expected these little alpha particles to just zip right through, maybe getting nudged a tiny bit. But yeah, that is not what happened. Sure, most of the particles flew straight through, but a tiny, tiny fraction, we're talking like 1 in 8,000, got deflected at huge angles. Some even bounced right back at them. Rutherford himself said it was as incredible as if you fired a 15-inch cannonball at a piece of tissue paper and it came back and hit you. Just unbelievable.
So, what's the big takeaway here? This crazy result could only mean one thing. The atom was not a soft pudding. It had to be almost entirely empty space, but with a tiny, incredibly dense, positively charged core, the nucleus. And this was revolutionary. It meant the solid world we see around us is mostly an illusion. And just like that, the first piece of our quantum puzzle snapped into place.
But, okay, this new model of the atom, this sort of mini solar system, it created a whole new headache. According to the classical rules, an electron whipping around a nucleus should be constantly giving off energy. That would cause it to spiral inwards and crash into the nucleus in less than a second. So the question was, why don't atoms just, collapse? Turns out, the next clue was hiding right in front of everyone, in the light that atoms give off. If you take a gas like hydrogen and heat it up, it doesn't glow with a smooth rainbow of colors. Nope, it only gives off light at these very specific, sharp lines of color. It's like a unique barcode for hydrogen, and that was a dead giveaway that some hidden rule was at play, stopping electrons from having just any old energy they wanted. And the solution was, well, it was a totally radical idea called quantization. Thinkers like Max Planck and Niels Bohr basically said, what if energy isn't a smooth ramp? What if it's a staircase? An electron couldn't have just any energy. It could only exist on specific energy steps. And when it moved between them, it leaped instantly without ever existing in the space in between, like teleporting from one step to the next. And this is such a cool way to see why this happens. If you stop thinking of an electron as a tiny ball and start thinking of it as a wave that's spread out along its orbit, it all makes sense. The only stable orbits are the ones where the electron's wave fits perfectly, with a whole number of wavelengths, just like a guitar string, which can only vibrate at specific notes. Any other orbit, and the wave would just interfere with itself and fizzle out. Alright, so electrons are waves. Got it. But just when physicists thought they were getting a handle on things, the detective story took another completely bizarre turn. It turns out the very nature of reality was about to get a whole lot stranger. This was a full-on, two-pronged attack on common sense. First, an experiment called the photoelectric effect showed that light, which everyone knew was a wave, could also act like a tiny particle.
Then, a physicist named Louis de Broglie just flipped the whole thing on its head and suggested that if waves can be particles, then particles, like our friend the electron, must also be waves. It was like everything in the universe suddenly had a split personality.
And that photoelectric effect? It was the smoking gun. See, when you shine light on a metal plate, it can knock electrons loose. But it worked less like a gentle wave washing over the metal and more like a stream of tiny bullets. These little packets of light, called photons, each one carrying a tiny specific punch of energy, were responsible. It was particle-like behavior, no doubt about it.
So you can see how this leads to the big, frustrating question at the heart of all this, right? What is an electron? Or a photon? Is it a particle? Is it a wave? Which one is it really?
And the answer is just mind-bending. It's both. And it's neither. It all depends on how you look at it. The act of measurement itself seems to force the object to pick a side. If you design an experiment to find a particle, you find a particle. If you design one to find a wave, you find a wave. It's like its reality is literally tied to the act of us observing it. Crazy, right?
Okay, so we've got empty atoms, these weird quantum leaps, and this particle/wave identity crisis. How on earth does this all fit together? Let's take a look at the new rulebook physicists came up with to describe this hidden, bizarre reality. Rule number 1 of the new quantum rulebook, and this is a biggie: throw certainty out the window. At this level, you can't say for sure the electron is right here. Instead, all you have is a cloud of probability, which is described by something called a wave function. It's more like a weather forecast for the particle, telling you the odds of finding it in any particular spot.
And this is the engine that drives it all. The famous Schrödinger equation. It's the master recipe for quantum mechanics. It won't tell you where the particle is, but it will tell you with perfect precision how that wave of probability, that probability cloud, is going to behave and change over time.
And the things this equation predicts are just out there. For example, something called quantum tunneling. Imagine you roll a ball at a hill, but it doesn't have enough energy to get to the top. In our world, it's simple. It rolls back down every single time. But in the quantum world, there's a real, non-zero chance the ball can just, poof, appear on the other side of the hill.
And what's so cool here is you can actually see how this works. The probability wave of the particle doesn't just hit the barrier and stop dead. It actually leaks into the barrier a little bit. And if the barrier is thin enough, a tiny bit of that wave can leak all the way through, which means there's a chance, a real chance you'll find the particle on the other side. Impossible, but true.
You know, this whole world of probabilities leads to some of the most famous head-scratchers in all of physics. The idea is that until you actually make a measurement and collapse that wave of possibilities, a particle exists in all its possible states at once. This is the whole idea behind Schrödinger's cat, a cat in a box whose fate is tied to a quantum event. According to the rules, that cat is literally both alive and dead at the same time until the moment you open the box and look.
And that, right there, brings us to maybe the biggest, most profound question of them all. If the entire world is built from these fuzzy, weird, probabilistic quantum parts, why does everything we see and touch seem so solid, so predictable, so normal? That dividing line between the quantum world and our classical world is still one of the deepest mysteries in science. It's the ultimate cliffhanger. And it forces us to keep asking a very simple but very complicated question. What is reality, anyway?